process state and state transition. So here you consider any process or any applications, it will be during the execution phase, it will be in different states. States in the sense, as you can see in the diagram, the created state, ready state, running state, block state, or the completed state. There will be different states, or in general what we call it as starting from the process initiation or till the end, till the termination. The entire process is known as the process life cycle. Okay, so under this process life cycle, this process of the applications will undergo various state changes. Okay, it traverses through a series of states during its transition from newly created state to the terminated state. So starting from the created state, whenever you call an application or whenever you want to run that particular applications, what we do is we just click on suppose say consider your phone. If you want to open WhatsApp, you want to run that application, just click on it. So it will start executing, right? Like that, any application, you'll just select it. So what happens, as I told you in the last session, the application program, whatever is there in order to serve that application or serve that process, will be stored in a particular memory of a section of a memory will be allotted for that application. Okay, so that application, the program will be stored there. Once it is done, that is nothing but created. Okay, initial application will be created, and next, as it stores in a particular memory, okay, various so resources should be allotted for that in order to execute that particular application. That application may require, or that process may require various resources. So basically from the created state, it goes to the ready state. Ready state in the sense, it is nothing but it tells that the memory is allotted, the required resources is allotted, everything in order to service that particular application is ready. Okay, so once it enters that ready state, uh, next state is nothing but it enters the next change of state. Once all the resources are available, the process enters the running state. Okay, running state, it totally depends on the CPU. In order to execute a program, a CPU should be allotted. As you are aware that in any processor or the controller, we have a single CPU, like a single controller. So basically, what happens? There should be some scheduling strategies, because the process which will be in ready state, there may be n number of processes in a particular system, in a particular embedded system. There may be more than one processes will be in the ready state. So these processes should be scheduled, right? Execution of these processes should be scheduled. That is, CPU should be shared along with this process. So once the scheduler schedules the execution, then there will be a transition from the ready state to the running state. Running state is nothing but it is the process during which whatever process was in queue already set, it will start its execution. Okay, it will start the execution of that particular application. Okay, as you are aware, in order to execute, it requires all the resources. All the resources will be allotted, then only it enters the running state. Now, during this state, during the running state, there may be a chance that one execution may complete. Okay, all the resources are there, everything is available, it may complete its execution. So in that case, the next state will be completed state, execution completion. Next is nothing but the termination state. Or there may be certain other factors, like, say for example, interrupted or preempted. Interrupted or preempted in the sense, during the running phase, running of a particular process, suppose if any high priority task comes to the ready state, or high priority process comes to the ready state. As you know that whenever an high priority task or the high priority process comes to a system, uh, it executes always, it is nothing but an interrupt will be generated. So therefore interrupt, the high priority interrupt should be serviced at any cost. So in that case, the present running task or the process will be stopped, and then the high priority task will be executed. So therefore, during the running of process, if any high priority task occurs, then the running of that previous process will be interrupted. Again, it enters to the ready state, and the high priority task will be in the running state. That is one thing. And suppose preemption in the sense, as I told you earlier, each processor CPU has to be shared. So there may be different scheduling strategies followed by the operating system. So based on the scheduling strategies, sometimes pre-emission can take place. Say for example, round robin. Round robin in the sense, time will be allocated for each process. Whichever process is in the ready queue, Okay, equal amount of, say for example, I'll assume that there are 5 processes in the ready queue. So if the round robin scheduling is followed, a time slice, say for 5 millisecond is a time slice. It means that process P1 will be executed for 5 millisecond. After 5 millisecond, P1 will be pre-emitted. Next, P2 will enter from the running ready state to the running state. It will be executed for 5 millisecond. After 5 millisecond, again it goes to the ready state. So this process, okay, this process continues. That is nothing but the pre-emission of the task continues. Okay, so these are the two cases where the state may change from running to the ready state. One is interrupt and other one is a pre-emission. And fourth, one more thing possible over here is during the running process, there may be a chances that the resources may not be allotted, or the resources in order to execute, in order to service that particular application is not available. So resources like maybe various input devices or maybe output devices if you want to display or display unit is required. Suppose if it is not available, if it is busy doing some other task, in that case also there will be a transition from the running state to the block state. It enters the block state because the entire process is blocked due to the non-availability of the resources. Okay, then after that from the block state again shared resource, if the resource is acquired or if the resource is available, then from the block state it goes to the ready state and from the ready to the running state. So this is the overall process, what we call states, what we can represent during the execution of any process. So these are the different states as I have already explained you. Go through the next slide. Next is nothing but the thread. Now what is thread? Thread is the pre-emittive that can execute the code. Okay, thread is also a sequential flow of control within a process itself. These threads, the difference between a thread and process, as you know, it is the entire application. A thread is again the part of that particular process. Okay, in a process, there again it may be divided into various processes. In that case, what happens? It is a part of a process uh, where what we call it as a lightweight process. Okay, like that process may have various threads. Okay, different many threads may be there. Okay, different threads which are the part of the process share the same address space, meaning that the share of the data memory code as well as the heap memory. That is nothing but whenever a process comes to the memory, what happens, a certain memory is allocated for that particular application or particular process, right? Along with that memory, in the sense part of data memory, part of the code memory, a part of the stack memory will be allotted. Here also same thing, the thread is the part of the process itself. In order to complete it, various threads, various subdivision of the programming will be done. Okay, it is a part of the process. Along with that, see here, then the entire process, okay, whatever data is memory is allocated, whatever code memory is allocated, same memory is meant for that thread also. Again, a separate memory will not be allocated. And one more thing, the stack memory is there, no? What the main stack memory has been allotted to that process. These stack memory will be again subdivided. Okay, remember the stack memory of the process. Okay, stack memory of the process will again it will be subdivided, okay, into form of a threads, and each memory will be allocated to each threads. Okay, each memory of stack is allocated to each thread. That is nothing but the execution phase. Okay, so thread maintain their own thread status, that is CPU register, program counter, as well as the stack. That is also one of the important thing. It is a part of a process. Again, thread is also, we can consider the sub part of the main process. It will have its own status registers like a CPU register values and various things, as well as a program counter value. Every thread will have its own locations, its own program counter, its own registers. Okay, same as that of process. So this is nothing but a basic concept of multi-threading. So here you can observe the entire Wiggle circle is nothing but a process, or what we call it as a task or a process. Okay. So as we have seen, each process will have, whenever the process comes for the execution, a particular memory will be allotted for that. That is nothing but the code memory will be allocated, data memory will be allocated, as well as the stack memory will be allocated. Along with that, various working registers will be allocated for that process. Now, inside a process, we can have various threads. Okay, you can observe here, this is single process. Under the single process, we can have various n number of threads in order to complete the execution of that process itself. Therefore, that is nothing but whenever the thread is created, out of that memory itself, the code as well as data will be shared commonly, but the stack will be divided into various threads. The stack memory, whichever is available for that entire process, will be divided into various threads, as well as it is divided, the registers will also, the working registers will also be divided. Along with that, the program of that thread, say thread 1, thread 2, thread 3. Okay, it is a part of the process, but here because of this, what happens, we can, since all this may not be dependent, or it can be an independent. If it is not dependent, then we can execute this in parallel, right? Threads can be executed in parallel. Okay. So use of multiple threads to execute the process brings the following advantages, that is better memory utilization. Multiple threads of the same process share the address space or the data memory. This also reduces the complexity of the inter-thread communication, since variables can be shared across the threads. Okay, since the process is split into different threads, when one thread enters the wait state, the CPU can be utilized by other threads of the process. That is, whenever during the execution, what happens if the resources are not available to execute that thread, or if it is waiting for some other resources. In that case, what happens? This can be enter the thread whichever is being executed. It can enter the block state or the ready state, and the next threads which are in queue can be executed. So overall execution speed can be improved. Right? It is not the efficient CPU utilization, as well as CPU is engaged all the time. These are the different thread standards available in the syllabus. Only that POSIX standards are there. That is nothing but it stands for Portable Operating System Interface, which deals with the real-time extensions, and POSIX, that is 4A standard, that is a standard, deals with the thread extensions. We'll just go through this small programming. This simple example is given. We'll just go through it later. So basically, this POSIX standard library for the thread creation and management, what we call as pthreads. Okay, it has a library, that is pthread library, defines a set of POSIX threads creation and management functions in C language. Using this library, we can divide the entire process into various threads. Okay, we need to do in the entire, while we write a program, it's there itself, we can have a provision to what we call define a thread. Okay, define a thread, how it has been placed, and when to call that thread. So all that can be initialized. This is one of the examples, that is POSIX thread. Along with that, we have for Windows operating system, there's a thread known as Win32 thread, is also a library, as well as Java thread. Okay. So the basic difference between a thread and a process, thread is nothing but a single unit of execution, and it is a part of a process. Okay, it is nothing but a part of the process itself. Whereas process is a program in execution and contains one or more threads. Okay, thread does not have its own data memory and heap memory. It stays the data and the heap memory with other threads of the same process. For the whenever the process gets the data and the heap memory, same memory will be shared along various threads. Okay, process has its own code memory, data memory, and the stack memory. Okay, a thread cannot live independently, it lives within the process, whereas process contains at least one thread, it can live independently. There can be multiple threads in a process, or the first thread calls the main function and occupies the start of the stack memory of the process, whereas threads within a process share the code, data, and the heap memory. Each thread holds a separate memory area for the stack. So threads are very inexpensive to create. Processes are very expensive to create, involves many OS overheads and all. Whereas context switching is inexpensive and fast, because it is within the process there will be switching. So we can say it is inexpensive. Context switching in case of process, it is complex and involves a lot of OS overhead, because the entire application will be switched from one process to the other process. If a thread expires, its stack is reclaimed by the process, right? If one particular thread execution is not at all done, if it is expired, then again we can restart easily, because it will be within the process itself. We can get one more stack, a separate stack, and then execution can be restarted. But whereas if a process dies, the resource allocated to it and to it are reclaimed by the OS, and all their associated threads of the process also dies. Right? So this is the major difference. In case of whenever the process dies, the entire thread will also die. Okay. So this is about process threads and applications.